Black holes are one of the universe's most fascinating phenomena. They captivate our imagination with their mystery, power, and the unknown. But what exactly are black holes? How do they form, and what eventually happens to them? In this video, we'll explore the life cycle of a black hole, from birth to death. Along the way, we'll look at real-world examples of black holes and what they teach us about the universe. Black holes begin their lives in the hearts of massive stars. When a star many times the mass of our sun exhausts its nuclear fuel, it can no longer support itself against the force of gravity. The core collapses, triggering a supernova explosion. If the core's remnant is sufficiently massive, it will collapse into a singularity, a point of infinite density, forming a black hole. For example, consider the famous star Betelgeuse, which is expected to end its life in a supernova. If Betelgeuse's core is massive enough after the explosion, it could become a black hole, adding to the cosmic tapestry of these enigmatic objects. Not all black holes are created equal. There are several types, each formed in different ways. Stellar black holes, like the ones formed from collapsing stars, are the most common. But there are also supermassive black holes, found at the centers of galaxies, which contain millions or even billions of times the mass of the Sun. A prime example of a supermassive black hole is Sagittarius A, located at the center of our own Milky Way galaxy. This behemoth has a mass equivalent to about 4 million suns, and it plays a crucial role in the dynamics of our galaxy. There are also intermediate mass black holes, which are a bit of a mystery, as they sit between stellar and supermassive black holes in size. Some astronomers believe these could be the missing link in black hole formation. Finally, there are primordial black holes, which are hypothetical remnants from the Big Bang. If they exist, these tiny black holes could have formed in the earliest moments of the universe and may provide insights into the birth of the cosmos. A black hole is more than just a void in space. It has several key components. The singularity is the point of infinite density at the center. Surrounding the singularity is the event horizon, the boundary beyond which nothing, not even light, can escape. Outside the event horizon, the black hole's immense gravity warps spacetime, creating phenomena like gravitational lensing. Gravitational lensing is an incredible effect where the light from stars and galaxies behind a black hole is bent around it, allowing us to see objects that would otherwise be hidden. This effect was famously observed in the galaxy cluster Abell 370, where the black hole's gravity acts like a cosmic magnifying glass, distorting and magnifying distant galaxies. Einstein's theory of general relativity tells us that gravity is the result of massive objects warping spacetime. Black holes, with their immense mass and density, create extreme distortions in spacetime. Near a black hole, time slows down, and space is stretched in unimaginable ways. This effect is vividly illustrated in the movie Interstellar, where the crew experiences severe time dilation near a supermassive black hole called Gargantua. While it's a fictional example, the science behind it is grounded in real physics. Near a black hole, time indeed passes differently, making these regions of space incredibly intriguing for both scientists and science fiction enthusiasts. The event horizon is the point of no return. Once something crosses this boundary, it is forever lost to the black hole. But what lies beyond the event horizon? This remains one of the greatest mysteries in physics. Some theories suggest that matter is crushed into the singularity, while others propose the existence of wormholes or even pathways to other universes. One of the most famous black holes is Cygnus X1, a stellar mass black hole in a binary system. Cygnus X1 was the first black hole to be confirmed by observational evidence, and it's been studied extensively to understand what happens at the event horizon. While we can't see beyond this boundary, the behavior of matter and energy near Cygnus X1 has provided valuable insights into black hole physics. While black holes themselves are invisible, we can observe their effects on surrounding matter. Material falling into a black hole forms an accretion disk, heating up and emitting powerful radiation as it spirals inward. In some cases, black holes eject matter in the form of relativistic jets, which are among the most energetic phenomena in the universe. The galaxy M87 is home to a supermassive black hole that produces a spectacular relativistic jet. This jet is so powerful that it extends thousands of light years into space, and it's visible across multiple wavelengths, from radio waves to X-rays. The first ever image of a black hole's event horizon, captured in 2019, was of this very black hole, marking a significant milestone in astronomy. Black holes often form in binary systems, where they orbit a companion star. These systems are fascinating because they allow us to study black holes indirectly. As the black hole pulls matter from its companion, it creates an accretion disk, which can be observed with telescopes. The gravitational waves produced by the interaction between the black hole and its companion have also been detected, opening a new window into the study of black holes. LIGO's detection of gravitational waves in 2015 confirmed the existence of binary black hole systems. The event, known as GW150914, was the merger of two stellar mass black holes, each about 30 times the mass of the Sun. The resulting black hole was briefly 50 times more powerful than all the stars in the observable universe combined, showcasing the incredible energy of such events. Black holes aren't entirely immortal. Over incredibly long timescales, they can lose mass through a process known as Hawking radiation. This radiation, predicted by physicist Stephen Hawking, occurs due to quantum effects near the event horizon. Over time, this causes the black hole to evaporate, shrinking and eventually disappearing completely. For example, a black hole with the mass of our Sun would take about 10^67 years to evaporate through Hawking radiation, far longer than the current age of the universe. Smaller black holes evaporate much faster, though still over astronomical timescales. This process, while slow, shows that even the most powerful objects in the universe have a finite lifespan. As a black hole evaporates, it leaves behind nothing but a faint imprint on the fabric of space-time. The exact details of what happens in the final moments of a black hole's life remain a topic of intense research and debate. Some theorists suggest that black holes could leave behind stable remnants, while others believe they vanish entirely, leaving only radiation behind. The study of black holes, from their birth in stellar collapses to their potential evaporation billions of years from now, offers us profound insights into the nature of the universe. These enigmatic objects challenge our understanding of physics and continue to inspire scientists and the public alike. As we learn more about black holes, we're not only uncovering the secrets of these cosmic giants, but also gaining a deeper appreciation for the universe itself. Don't forget to subscribe and hit the like button to stay updated on more cosmic wonders and the latest discoveries in our universe. Your support helps us explore the mysteries of space together.